Hello.
Hello, sir. Good morning.
Morning. Can you hear me?
Yes, sir.
Okay. Can you see the slide?
Yes, sir.
Okay. Great. I think it's time, 10 o'clock, right?
Yeah, right. You can start.
Thank you. So I did not get the questions from yesterday's Zoom chat. So one of you said that you will send me, but
Santosh, sir.
So it has not happened. So
Okay, sir. Let me check and send you today. Today evening before.
yes. All right. Okay. Good morning, students. I hope you can see my screen here. I sort of stopped here, I think, saying that the galaxy has stars, gas, and also the dark matter in terms of the dark matter halo around the galaxies, and which contain basically most of the baryons. From the flat rotation curve, which I showed in this plot, one can actually deduce that if BC circular velocity is actually constant, this can be used to show that the rho, the density, is proportional to 1 over r square. So this is a very interesting solution. So this is actually called isothermal halo, or rather singular isothermal halo solution. Because at r equals to 0, this now blows. Okay. So, and also this will have the mass of the halo within a radius r is proportional to r, which means that r goes to infinity, the mass will go to infinity. So this is also there's not a very physical solution for the dark matter halo profile. So this has been modified to look like that rho equals to some rho naught 1 plus, in a simplified way, it's like r square by rc square. So rc is some kind of a co-radius. Okay. So for r less than rc, density is almost like rho naught. Okay. So if you plot here, as I said, so this is the rho dark matter, and this is the r. So maybe we'll go like this. So we get a very core radius, like this, almost like a constant. So this is a core profile. Okay. So this is called pseudo isothermal halo. Pseudo isothermal halo. All right. Now this is being used to model dark matter halos in many galaxies in observation. Okay. Once you have a flat rotation curve, you can use this dark matter halo profile to model the observation. Okay. However, the dark matter halos that are produced in the cosmological simulation, they are slightly different. They are of the profile when the rho is like what I have written here, like rho naught divided by r plus Rs into 1 plus R over Rs to the power 2. This can also be, I think, modified like I can put like this to the alpha and this is 3 minus alpha. Okay, so this is, I think, called the generalized NFW. Sorry. Okay. For alpha equals to 1, this is NFW. Okay. So what's the difference between this and this? Difference between this and this is that when R goes to 0, this one, NFW value still like no blows. Okay, so at large R, it will go as when R is greater than RS. Now RS is some kind of a scale length in the problem. It's like a co-radius also. Okay. So this dark matter halo are modeled by two parameters. One is the central density and another the scale length. Okay. Similarly, central density and a co-radius. So when R greater than RS, you can see that rho is proportional to 1 over R cube. Okay. And when R is greater than RC, then this is proportional to 1 over R square. Okay, this is like steep. Okay. Now, and the important part is at the center. At the center, the dark matter halo profile would be like cuspy, okay, with a high density. So this is called the cusp. This is O. So this is a difference or the disagreement between the simulation which produces dark matter halo from the initial conditions like CMB, like initial condition, which goes into the structure formation system. And then what you produce in the, then what you model using the observational data. Okay, observational data don't seem to fit well this one, okay, because of the cusp. Because the flat rotation curve is so nicely done with 1 over R square profile, not with 1 over R cube. So this became like a controversy, like disagreement is still on. So there are various things. People think that maybe the galaxy the dark matter halos are produced in cuspy, and later on the cusp is like destroyed and like sort of made flattened, and that's why you see like in a core profile many things like in actually in the context of modeling this dark matter. All right. So this is very briefly about the dark matter halos in galaxies. So our galaxy in general is made up of, I will erase this. It's made up of stars, gas plus dark matter. Okay. Now the first thing that we that you have sort of got a feeling for what are the kind of the distribution, the star light in the galaxy. So we did that, for example, if you have a spiral galaxy, then the stars light follow an exponential distribution. And then if it is elliptical galaxy, then you have a Sarsic profile, light distributions. Okay. Then I think I also have showed you the distribution of the gas profile in the galaxy. Okay. If you have forgotten, which is very likely, then this is the kind of, this is in this, you see the surface density of neutral hydrogen gas all the way from center to very outer radius of the galaxy, like 15-20 kiloparsec. For many, many galaxies, these measurements were done, right? And the profile looks really wild here, right? And astronomers try to like fit with the profile, and the green is some kind of like you can see, this is the Milky Way profile. Okay? Green is the Milky Way profile, and where does this come from? So the gas surface density is also being modeled as some kind of exponential profile. But the catch is, in terms of a minus R over R, this is the important part here, which is R25. And this is here exponential of minus R over R E, some kind of a scale length. Sarsic profile, of course, like this is like minus Bn R over Re to the power 1 over n minus 1, okay, like that. So it's like these are the kind of a profile, the density profile, the surface density profile of this corresponding component. Okay, in spiral is like that, elliptical is like the gas is like that. I said the catch is here between this and this. The stars also follow exponential profile, exponentially declining surface density. The gas also exponentially declines surface density. But the R25 is the definition of R25 is that it defines the radius of a galaxy. The radius of a galaxy, you can think about like a spiral galaxy, the center. If this is the R25, okay. R25 is where the surface brightness of the stars fall at 25 magnitude per arc second square. That's the kind of value in something called in a blue band. Okay, so originally, idea was that galaxy nearly ends here at that radius, because after that it's mostly like faint noise, like something like if you look at these images here, you would say like this is where like kind of the R25 is. So nothing almost there. In galaxy sort of like it's a height like with the sky sometimes. So R25 is that radius, but R25 when you convert into just a scale length is around 4 to 5 scale length. So it is quite a large number. Okay, so it's like more like a flat distribution, and you can see that in Milky Way, if we do that, then it's almost like a flat distribution. So like a constant surface density. So that's the gas. So with this idea, now we want to move ahead with the understanding of the motion of the stars in the galaxy. Then we'll be in a position to understand what kind of physics that would be applicable to further enhancing our understanding of the galaxies. So it seems that first we should have an idea about the how many stars are there in a galaxy, and that's not very difficult, because if you know, um, you will be surprised that that we have this, our sun is a star, G-type star, and the next star, nearest star, which you all have heard of, the Proxima Centauri, at a distance of 1.3 parsec. Within this volume, there is no other star. Okay, within this volume, there is no other star. So basically, it's like almost one star within this volume made by 1.3 parsec radius. Okay, so that gives you some kind of a number density of stars in the galaxy. Rough estimate. Okay, if you take the typical, if you take a typical, what is the volume of a galaxy? Now I've said that the typically the Milky Way galaxy size, stellar disk, ends around 15 kiloparsec. It has a thickness of around 1 kiloparsec height. So I would think okay, something like this. Like a Milky Way is a big spiral galaxy, like a disk-like galaxy. Okay, and it has this thickness which is around the 1 kiloparsec. Okay, 1 kiloparsec is distance. You can simplify, say like 10 kiloparsec. Okay, you can calculate the volume, which is like pi into r square into h. H is 1 kiloparsec. Put it in your numbers. You will see that number is like quite large. So you multiply by the number density, you will get a rough estimate of the number of stars in the galaxy. Okay, and that number comes out to be n is of the order of 10 raised to power 11 stars. Quite large. So now we want to know that all these 100 billion stars in the galaxy, how are they moving? And if we can understand that, that's like already like quite something. Okay. This part. So considering that all these 10 to the 11 stars are like a sun-like stars, where again the rough estimate, you can always do order of magnitude estimates, which are useful, and I think you should always learn to do that. So there are variations in the stellar properties in the galaxy. Some stars are big, massive, some stars are small. So there are lots of like, but we can say that okay, all stars are like sun-like stars. Okay. Then what you can do is that you know the number density now, n, okay, which is around 1 star per parsec cube, roughly. 1 per parsec cube. And then you have sun-like stars, so you know the radius of the sun. So you can do the collision cross-section, right? The collision cross-section, sigma is so you can determine the collision cross-section by the which is the area of this, like our sun is the radius of the sun. Okay, and then you can calculate the mean free path. Okay, I have this number somewhere. Show you. Yeah. You can see that if you make the collision cross section and then calculate the simple mean free path, so mean free path of a star in a galaxy is really large number. This is kind of an absurd. Okay, so in other words, it means that the mean free path of a star in the galaxy is, even if you make error, you can make correction and whatever. This is very large compared to the size of the galaxy. And this is the opposite for the gas molecules in the room, okay, which is, I've put it on the left side. And in the case of a gas molecule, you will, like, one nitrogen molecule would not even go an angstrom path length, before which it will do like a head-on collision with another molecule. But for the star, when they go around in the galaxy, there are many other stars which will go around at the same time, but nobody collide with each other. Okay, so there is no head-on collision, which is very rare event in this. So one thing that we learn from this simple estimate is that head-on collision in galaxies are rare. Head-on collision basically is not happening. Rare. However, you can imagine that when a star moves with a certain orbit, even there is another star, right? It goes. This star would try to deflect, right? It will try to bend like that, because that is going to happen. Now, what we don't know is how much it bends, like these, like these. We don't know. So you can imagine a star. So there is something called the strong encounters. So as I said, since the head-on collisions are not important, then the stars will, as it moves in the galaxy, it will encounter with other stars, right? So there can be deflection this way, and mostly deflections, because they are not going to do the head-on collision. Now, so there is this. In the encounter, there are two different kind of encounters. One is a strong encounters, and weak encounters. Okay, weak encounters. In the strong encounters, is such that the star, imagine, comes with a energy half mv squared. Okay, imagine when it goes to at the closest distance of our collision. Okay, then the rate of change of this the potential energy, the energy of the star, is of the order of the initial kinetic energy. Okay, at least of the order of initial kinetic energy. So you can think about this is gm squared by r collision is of the order of half mv squared. If that happens, then the star is supposed to have undergone a strong encounter. Okay, we have undergone a strong encounter, and you can find out what is the strong encounter radius. Sorry, gm by 2 v squared. right? Did I do it right? Or no? 2 gm by v square. So that would be a strong encounter ATS. So one can also calculate this strong encounters time scale. Okay, so the characteristics time scale in the same way we can do like because this will give you some kind of a cross section around of this radius, and then you can also calculate the collision time. The collision time is written here is 1 over n sigma into v. 1 over n sigma into v is the length scale, and then that's how you get the time scale typically. And this collision time seems to be seems to be much greater than the Hubble time. So you can take the v is like around 20, 30, 50 kilometer. N is like 1. You can change a little bit. It will not change this 10 to the 13 much, okay? Unless you go to very absurd number. It's possible. Okay, so this gives you an understanding that the strong encounters are also very unlikely during the lifetime of a galaxy. During the lifetime of a galaxy, it can't be more than the Hubble time. Right? So I'll bring some water. Just a moment. Sorry, back. So it turns out that the strong encounters are also not important. How about the weak encounters? Weak encounters are actually interesting. So I'll do the same picture. Weak encounters will not get into the derivation because it's a bit lengthy derivation here. And just the concept, I think you should like. Imagine a star goes around in straight line path with an initial velocity v. Right? If there is some like a star, so again this will be some deflection. What's wrong? So imagine this is like an impact parameter like b. So one can actually calculate this star will deflect the star towards it. So there will be change in the vertical velocity of the star. It will pull by. right? And then as the star goes around the galaxy, there will be stars from this side, so it's basically, there can be here, there can be here, there can be here, it will deflect this way, maybe this way, this way. There can be random deflections. If we try to add all of them, the net is basically 0. You can safely assume that net is 0. However, if you don't add the net, but you add this in terms of square and take the average for all such encounters possible. So this basically similar to like a Coulomb interaction, in which there's like Coulomb logarithm comes here. So this delta V square becomes non-zero. Okay, if you do this. Now you can imagine that a star goes around the galaxy and it this deflections happening, and over some time, if we integrate over all or add it up over many time periods, then within a time, let's say some time, then with this time, this change, net change of delta W will be of the order of the initial velocity square. Okay, there, because it's accumulated over this. So you can basically integrate over time. Now, the time scale over which this happens in a galaxy is called the T relaxation. Okay, this is a very important time scale that comes out of this analysis. Of course, there are time scale also there. For example, this is the collision time scale. Okay, but it's very large. It turns out that the T relaxation time is n over log n multiplied by T crossing. Now, what is n? N is of course the number of stars in the galaxy. Okay, number of stars in the galaxy, and to time the crossing time. What is crossing time? So imagine your galaxy is let's say a spherical galaxy of size, let's say r. Okay, it has n number of particles, and average velocity is let's say v. That's a mean velocity in that. Then the crossing time simply of the order of r over v. Okay. Now this is very important in a sense that it says that you can see that over relaxation time, the net change in this small deflection that happens will add it up and will be of the order of v square. Okay, of the order of initial velocity, which means over this time, galaxy has almost forgotten what was the initial thing it came from. So this is the how basically this small encounters sort of makes it a relaxation in a galaxy in a sense, in some sense, and this relaxation time simply depends on the number of stars or in the galaxy and the crossing time. Now, this is not just true for the galaxy, because this can be applied on any spherical systems, spherical self-gravitating systems, when there are n particles acted by the gravity here, only gravity. Okay, then one can actually show that you can calculate this time scale, relaxation time scale, for example, from a globular cluster, where typical size of the globular cluster is about a parsec, and the typical velocity is around 10 to 20 kilometer per second, and then typical number is around 10 to the 6 or 1 million stars in a globular cluster. Okay, you can do that. Globular clusters. You can also think about a galaxy cluster. Okay. Galaxy cluster, when typical galaxy cluster have 1,000 galaxies, not typical, but only the rich clusters have thousands of galaxies in that. The size is about 1 megaparsec. Typical velocities would be like a few hundred kilometers per second, like 300, 400, or even go to 500 kilometers per second. And you can calculate the relaxation time. So if your time scale, relaxation time scale, is of the order of Hubble time or less, then it means that you need to worry about encounters in the galaxy. So if T, your time scale for this your system, if less than T relaxation, if T relax is less than equals to T Hubble, which is around 13.7 billion years old, then this you need to worry about the encounters in the system, which means you cannot ignore encounters in the galaxies. However, if the T relaxation is much greater than the Hubble, then you can ignore encounters also. And it turns out that if you put number like 10 to the 11, which we just got from the galaxy, which is a little derivation that we did, and then you take the typical cross-section time, crossing time in a typical spiral galaxy like Milky Way, this relaxation time is much larger than the Hubble time. You can reduce that. It's not a big deal. You can take the R is equal to around 10 kiloparsec, and then velocity around 200 kilometer per second, and you can get this number. It's quite large. So in most cases in a galaxy, T relaxation is much larger than also Hubble time, like we have the strong encounters. So the hidden collisions is not important, strong encounters not important, weak encounters are also not important during the lifetime of a galaxy. Okay, so we have come to a conclusion is that the encounters and the collisions are not important in a galaxy. That's a very significant thing. By the way, the same thing is not true for globular cluster, okay, or even small star cluster. Okay, their collisions are important, okay, which is governed by this relaxation time. So this gives you some kind of a feeling right now that, hey, we have these 100 billion stars which going around the galaxy and they don't collide. Okay, they don't collide. Okay, that's the thing. They don't collide, which means that we can ignore safely collisions from describing a galaxy. Okay? And this leads you to an important step which allows you to say the galaxies are collisionless system like a collisionless plasma. Okay? Collisionless system. Then one can do many things with this. Okay, one can do many things. This, for example, we can think about that the galaxies are described by collisionless Boltzmann equation. Okay, in which we will not get into, but it's very essential if you want to understand further how to understand more and more about the galaxy physics. then you need to actually go through, but it may not, for some it may be like a little higher than what you have studied. So this is called the collisionless Boltzmann equation, which says that equals to 0. This F is basically the distribution function. F equals to F of R into V R and V are the phase space variable. Phase space variable of all the stars. Basically, if there are n stars, it will go from 1 to n like that. But in this case, this distribution function is called the one particle distribution function. So it depends on the single particle phase space coordinate. Okay. It comes from something even more general, which is like with the distribution function and the equation written for n particle distribution function, from where we have come to like this state. So this is the one particle distribution function. What it actually says, it says that if you have an infinitesimal phase space volume, okay, 6-dimensional, which I cannot draw, so it will be like a d3x and then d3v. So you can think about that this is like a phase space volume, okay, the 6-dimensional volume. Then you can have total number of particles here. So AF is like dn over d3x, d3v. In the limit, this infinitesimal volume element goes to like 0. So it's like becoming continuous, like a density. It's like a phase space density function. Okay, phase space density. So this equation actually tells you how the phase space density changes in the galaxies. The governing equation, so like partial differential equation. So it allows you to follow or understand how the phase space density is changing in the galaxy. Now, we don't know how the phase space density in the galaxy looks like, and neither we can measure in external galaxies, except now for the Milky Way, because of the Gaia satellite, which allows us to measure the 3 positions and the 3 velocities of 1 billion stars. So this is now possible. But even 10 years ago, it was not possible. Not 10 years, just pre-Gaia, it was not like very easy. There were some like scattered measurement. For example, Hipparchus did in the solar neighborhood of about 100,000 stars in the solar neighborhood, measured the positions and the velocity. And then there are some other surveys as well from the ground-based. It's extremely difficult and also like time consuming to measure each of the stars' position and the velocity accurately possible. Okay, you would be surprised to see the kind of the accuracy that we look for. So Hipparchus in the 90s, Hipparchus satellite, okay, that was the satellite which measured about 100,000 stars position on the velocity. That measured with something like a milli-arc second accuracy. Okay? 1 arc second and the milli-arc second accuracy. What Gaia is doing is like gone to like a micro-arc second accuracy. Okay, 10 to the minus 6 arc second and like now below. So that's quite an advancement actually. So it's just like, so so this is but for any external galaxy, this is a very difficult. Besides, this AF depends on the phase space variable, and our information is actually very limited. We don't have lots of information. Now I'll complete this. You see this phi? What is this phi? Phi is something, the potential, okay, the gravitational potential. So in general, the gravitational potential would be by 4 pi g rho, the density. This is the real density, not real density, the density which depends on the position only. Okay, the space density, not a phase space density. Now, this F, although it is not directly measurable quantity, except for this, as I said, for the Milky Way, but otherwise, F is related to the observed quantities. This space density is observed quantity, like I have already told you about the density distribution of stars in the galaxy. Okay, but of course there is that is a surface density, not a volume density. I'll come to that. I'll give you some feeling about what's the trouble. So rho is actually integration of F d3v. So if I take the distribution function and integrate over of the velocity space, I get rho as a function of r. That's the definition. So this quantity is observable quantity, which is like a measurable quantity. At least we can measure somewhere. This quantity is not measurable, but if you integrate over this is how we relate. Then you have mean velocity. V f d3v. It's like a moment of the first order moment of the distribution function. Similarly, you can have sigma square, which is like velocity dispersion. Okay, there you know that is v square minus, like that. The same definition would go from here. From v square, you put a v square here. For v, you know this one. So it's like a sigma square. So these quantities are observable quantity, rather we can measure. Now, of course, I do not know if you have already gone through a course in this lecture or somewhere else on how to measure. I have already told you how we measure this. I have not told how to measure this, and I have not told how to measure like this. But maybe like we will get into there. But one thing that you will see that if I put rho equals to here, so grad square phi is 4 pi g integral over f d3v, and we put in there as a phi using a Green's function method, then this becomes a very complicated equation to solve, like a real difficult integral differential equation. It's kind of very difficult. What else we can think about from here? So it turns out that we have very limitation here, and we will not be able to move forward with this equation just like that. We need to do something more to understand, go beyond. But first, let me give you a feeling about this rho, which is a volume density, and what you measure from the light distribution, which is in the projection, is the I, the function of R. So this, you can think about this is a volume mass density, and this is a light. So light, if you multiply by m over l, so you will get something like a surface density. Something like a surface density. But between the surface density and volume density, there is this, you have this, some kind of objects like that, maybe, right? So you get to see only one like projection of it on the sky. So you see like more or less like an ellipse. If you look into this way, you would get like basically a round shape. So depending on how the orientation of the objects, which we do not know, we see only the projection of that in the sky. Now from here to the original one, it's the most difficult part in astronomy. Okay, we don't understand. So this is a problem of deep projection. Deep projection. Except for sphere, we don't know a unique solution to this. It's a trouble. So it turns out that from to map from here to here, it's not easy. Although I multiply by mass to light ratio, which is a normal, which is some constant, we can get it from some other ways, but from sigma to rho is not difficult. So rho is what connects here. So because if you don't supply this, because this is the measurable quantity from F, but we have sigma. From sigma we need to go to rho. Along the line of sight, one can actually get easily like sigma, right? Sigma of R is like rho of, let's say, R, Y and Z and PZ. You integrate along the, imagine your Z axis is along the line of sight. I integrate along there. I can get sigma here, but the inverse is not, of course, easy. So this deep projection is an unsolvable problem. At the moment, we do not know. People try to do many things, but often we end up basically getting a solution which is only for the sphere, the spherical system. So it's a difficult issue. So we have to connect from here to here. What else? So we have two hurdles. One is the mass to light ratio unknown, and the deep projection, which is unknown, which allow the other doesn't give you how to estimate the total the volume density in the galaxy. And when you don't know the volume density of the galaxy, it becomes really, really difficult because if you don't know this, you cannot also get the potential. No? So there's a lot of unknown. The mass to light ratio and deep projection makes you solve these equations really, really difficult. Otherwise, this equation is not difficult to solve. But when you take an observational data and you want to say that, hey, let's estimate the galaxy's potential, right? And it turns out that this is the kind of a difficulty that you will face here. So the potential of a galaxy is also not easily derivable. I'm close to 11 now. I'll stop here and take questions. And in the next class, I'll try to give you some idea about the orbits of the stars in the galaxy and related to some evolutionary understanding of what is possible with the dynamics. Okay. So I think stop. It's 11 now. Stop sharing. Is there any question? Abhijit Das. Sorry, I do not know who.
Yes.
Yes.
Good morning, sir.
Good morning.
I have actually two questions, which are maybe a very basic ones. One regarding the dark matter distribution that you started with actually. So actually, I had the picture of dark matter that I had from the discussion is that dark matter is there and galaxies are embedded in the dark matter. But in today's discussion of yours, it looked like that the dark matter had had core and spreading out as the galaxy does. So uh, I think could I explain what I want to say? I mean, you talked about the as
So
the dark matter. There's a dark matter distribution.
yes,
Which has a core.
which has a core, which is observationally it is like that. So basically you have a galaxy like this is a spiral galaxy, and this is embedded in some kind of a like halo.
Yes.
Hollow. That's like kind of the picture that I imagine.
Yes.
And now this has a density distribution. So it will like take a radius from here all the way. So you'll have a density distribution. And that is the density distribution which I am talking about. So is there confusion in that?
Okay.
So this is like a dark matter halo. Like dark matter halo is bound by the virial radius.
Yes.
Virial radius. So which means you can think about that entire thing, because the dark matter halo mass often is greater than m star, which is the baryon mass inside, but not always. Not always. We know lots of cases. Then you can think about this is like also like a potential well of the dark matter, in which the baryons are here at the bottom of the potential well, because the density is high at the center, right? So it will be like this, so like qualitatively, right?
Okay.
Yeah.
Okay, I got that one.
Yeah.
So there is another question that is regarding the interaction between stars. That you talked about the strong encounter and weak encounters, and of course you ruled out any kind of encounters that can happen along with the collisions. Sir, but one question that is coming to my mind is that the most common stars that we see are binaries.
Yes.
So that raises a question regarding this visibility. I mean, this encounter, how this came about actually. Because ordinarily one would think that binaries might have formed when stars had some kind of encounters.
True. I get your point. So in my entire analysis, we ignore binary here. Okay. There are except Milky Way, we don't have much of any information about the binary fraction in galaxies. Originally, when these were going on, it was thought like the binary fractions in galaxies are not large, so one could safely ignore binaries. The binaries are like there in globular cluster, star cluster. Okay, but otherwise the binary fractions are not. Even when I'm talking about this distribution function, this is a one particle distribution function.
Yes.
Which came from the fact that we came from the fact, but we basically ignore the two particle distribution function. So one would add to this another epsilon into f of f2. Okay. But it is that we don't have any observational. My understanding is that binary fractions are not known very well in external galaxies. So most of the time it is thought that they are actually less abundant in galaxies in general than in globular clusters and turbulent, where you cannot ignore the collision. But also from the relaxation point of view, not the binary. But you are right that this analysis does not take into account of the binary. But I think it could be important to do.
Okay, sir. So thank you, sir.
I unmute Soham.
Hello, sir.
Soham Kapadi, please go ahead.
Good morning, sir. Sir, actually, I have doubt in this deprojection concept. Like,
Sure.
when we say ki, we have to deproject, we have only one projection and we need to produce the original configuration, right? So I was wondering, is it even possible? Because it is very similar to like we see the shadow of a stick and we try to guess its length, like original length. So
Yes.
is it even possible? Because some part of its original information is lost. So how do we get that back? Like, what are the approaches to even try deproject?
I think it would be really not easy for me to right now tell you with this limited time. So approaches is like what are the, because if we knew what approaches to do, then we would like go for a solution. But I know there are something people try to do. I erase everything so that. So one, if you think about a galaxy, right? It's like R rho as a function of R, some kind of a density distribution, and we know that our general idea about not about the rho but the surface density is bright at the center and falls with some fashion. It can be exponential, Sarsic, anything. With radius r, and this is the surface density. So what we get from here is that at the center there is a lot of mass, which will not depend on the deprojection. Okay, because whichever you deproject, this thing. So it is something that the bright at the center, faint in the outer part. So it's like so this gives you some idea about how the light is distributed in the galaxy. The next step, what people can do here is that think about rho is some kind of a n and then let's say some kind of a basis function yn of rv. So one can expand this hypothetical rho volume density as a basis function expansion, and then take the projections of this thing and try to solve the how do we say? So this kind of a basis function expansion, which basically solves the Poisson equation together, has been attempted in that, and then one of the basis function that has been used in galaxies, particularly in elliptical galaxies, are when the basis functions are Gaussian function, for example. It's some kind of like exponential of r squared by sigma squared. So you basically make the entire density distribution with a multi-Gaussian expansion like that. Okay, not very sure of like doing this properly. But yeah, so it's like that. So you take, so this is called the basis function expansion of the density distribution in that. And then since the basis functions like which you will be constructing for an image given or the density distribution given, one can actually, there's a like lot of nice properties. So basically Gaussian is like not very good. So I would rather will be a mathematical function. And that has been used to do this. And for elliptical galaxies, these seem to have worked well, but there are lots of like things. I don't think like I am aware of any valid projections. Like maybe you can think about the computer graphics where people like do this 3D graphics, but then they do like many realization of this. So you take one object and you take a number of like realization of that, okay, and maybe get some likelihood analysis approach which will best fit your observed density distribution. But there can be degeneracies as well, I am very sure. Okay. Okay, sure. Hello? Okay. I'll unmute Junik Sengupta.
Hello, sir. Am I audible?
Yes, go ahead. Yeah.
Thank you, sir. Good morning. The lecture was really fantastic. So my question was, as you explained the galaxies sit in a dark matter potential well. Now, each of these galaxies, each of them are associated with a dark matter halo. When these two galaxies collide, what happens to this potential well? What are the changes that the dark matter potential well suffers?
All right. So when the two galaxies interact, the dark matter particle are also collisionless. Okay, so that is even better actually, better than the star baryons actually. So the because if they're like candidate sterile neutrinos and the WIMP particles, so their cross sections are very low. So dark matter are even like a better example of a collisionless systems. So they don't collide, first of all, but they get mixed up. So one dark matter halo from the one and then another dark matter from another will be like mixed up, and often that is how actually dark matter halo grows from the very early time. Like when early universe, that these dark matter halos were small, like a mini halo. Mini halos. These mini halos like gobbled up like another dark matter halo part like this, and then they basically grown. So this is how probably I would think. So,
Okay, so I mean, when they're just colliding with each other, they're just getting mixed, and the potential will just rises. The dark matter potential.
Potential will get deeper and deeper.
Deeper and deeper.
Yeah, because they will get more massive. Then that's how the dark matter halo actually grows. In this is what you know from the simulation. Okay, because the dark matter halo often do not form with the big halo that we know today. Okay, they may, because there are lots of like there is a spectrum of like mass function, right? If you like sort of dn over dm, so like a spectrum. So it's like lots of like the low mass and then lots of high mass, depends on the what is the initial mass function of the dark matter formation, because when they collapse, so they may like form. Most of the time we think about they would form mini halos, and there's mini halos because of the gravitational interaction. They will like merge and then sort of get bigger. The same would happen. Okay.
Okay, sir, can you please suggest some books on this?
I look at often this Billy Tremaine. This is the master book for me, for graduate student, for beginners. I mean, it's a bit technical, but Billion Remain 2008. That's the, I think it's a good book to look at. And there's a lot of good physics and maths and there. So we can take a look at that.
Okay.
What Vaibhav Srivastav? I'll take 2 questions and then I will move. What? Was a fully moving star come near our solar system? The sun. So how the trajectory of the planet Ketan Singh, do you hear me? The question is, if a star comes very close to the solar system or sun, how the trajectory of planets deflect? This requires to do some analysis. How can I just say that there is no way. I think it will be easy for me to answer how the deflection would be. First of all, that doesn't happen generally because we Milky Way and Andromeda Galaxy may collide together. Okay, and we will not even know. That's how it is. That's the lessons that you have learned today. Head-on collision, strong encounters, even weak encounters are not important. Now, there is something that is important in this. So if the star comes arbitrarily close to a solar system, depending on the star's trajectory, there will be a lot of change in the potential. Okay. Sun, imagine only one star, one planet going around, and there is like another star, depending on what mass, and there is lots of free parameters here. So I don't think it's like, it could be very massive star, it could be same mass stars, it could be low mass stars. They could go orbit like this, they could go orbit like this, they could go on the plane. Okay, like there are many different orbital configuration possible. Imagine this is your sun. The star could go like this. Star could go like this. Okay, the star could just try to do a hidden version. Of course, that's not very likely. But other possibilities are like in each of these orbits, sun would feel a different thing, but the planets are stuck to the sun. Planets are stuck to the sun unless the perturbation is so strong that can affect the planet. Otherwise, it's not so easy. I don't think. There are various cases needs to be studied. I don't think I can give you a straightforward answer. Yes. Okay. And the planet just don't leave. It's very difficult. Why is it difficult? Each of this planet, when it goes around, okay, it has an energy, it has an angular momentum. There's also certain other integrals of motion which it obeys. These integrals of motion makes the star really fixed in the phase space. Okay, so it is not easy to destroy these integrals unless the perturbation is very strong. Very strong. Otherwise, it is not easy to destroy these integrals of motion. So the star planet may get pulled up, but leaving these things would require lots of energy to dump in, right? So that's not very easy. Okay, the next question. If we try to do, I read it here. If we try to do in-body simulation for a galaxy, crudely speaking, would it be enough to just specify the density of stars and size of the galaxy to ensure a collisionless system? What other parameters needs to be put in? Yeah, to simply say that the density is not enough, you have to put in the velocities also, because otherwise the stars don't move. You can arrange the stars in a certain way according to the density pattern, and then the star needs to move, so you need to give an initial velocity. How do you decide what velocity you give? So that's important for doing n-body simulation. The best way to do is basically construct a distribution function for the stars. If you construct a distribution function which solves the collisionless Boltzmann equation, then it is easy to, then it is ensured that the galaxy that you are simulating is a collisionless system. Okay? Bye everyone, see you tomorrow.